So thank you very much for having me. The last time I was in the Technion was for my PhD graduation ceremony in 2005. I had a very heavy cloak on. It was an extremely hot room and I almost fainted. So I hope you'll excuse me appearing in a t-shirt today in a nice air-conditioned room. We're going to talk today about permission blockchains. Permission blockchains are controversial, especially amongst people who are enthusiasts of cryptocurrencies. And we're going to talk about the various aspects of them. Using tomatoes representing accusations or questions that are thrown at the notion of a permission blockchain, and we'll be examining 8 tomatoes during the course of this talk. Some of them I think will hit home and some of them won't, and we'll talk about why that is. So the background to all this historically is that financial institutions looked at Bitcoin and were like very interested in it, very curious about it, but very quickly concluded, and other large companies concluded, that they could never use a system like Bitcoin, or at least they couldn't do so for the next decade or two. There's a whole bunch of reasons why that is. Systems like Bitcoin, like Ethereum, they have very low capacity. The governance models, which we've talked about in depth now, are pretty poor from the perspective of a conventional company. No one knows what the long-term cost is of transacting over these networks. The miners who are validating the transactions, well, we know who some are, we don't know who others are. They're in funny places that we might not be particularly comfortable with. The whole notion of having to hold a cryptocurrency in order to pay transaction fees to use these networks is something that many of these companies are uncomfortable with because they don't want to touch cryptocurrencies. Everything done on these networks is visible to the whole world, so that's obviously a big problem for companies that don't want everything to be visible. And they also you can't make these systems closed in terms of preventing who can participate in them. And the last thing is that because we have these large open blockchains, there's a whole lot of information in these blockchains and transactions in these blockchains that wouldn't be of interest to a particular set of companies that wanted to use it. So for all the reasons that cryptocurrencies are great for people that like censorship-free finance and that are looking at the kind of the idea of a new economy, for all of those reasons, they are unsuitable for conventional companies, banks and other companies that are interested in this kind of technology or elements of this technology. So what would a blockchain look like for a group of enterprises? Well, we're talking about a private shared database, okay? So it's shared between multiple companies, but it's private to those companies, and companies outside of that or people outside of that cannot see what's going on. It has what's called Byzantine fault tolerance. I'm sure we've talked about that a lot here over the past week. The idea is that this is a database that can be safely and directly shared between multiple companies, and even if there's some kind of programmer error in one of those companies or someone malicious in one of those companies, the network as a whole is resilient to that thing taking place. So if you look at traditional distributed databases, which have a fair amount technically in common with enterprise blockchains, they're not designed for a scenario where we can be resilient to someone deliberately doing something wrong or some kind of programmer error deleting data in the database. So it's not the same as a distributed database. We're talking about something which is more secure and more safe from the perspective of one organization relative to things being done in a different organization. Companies, of course, want to know what the capacity of their systems are. They want to know what the cost of these systems are. They want to choose who's validating transactions. It might be one company in the group, it might be all of them, or it might be a subset of them. They can stay away from cryptocurrency. They have the ability to administrate this network in some way to decide who can connect and who can't do so, and they need to be able to do so in a collective way. In other words, if the whole point of the system is to be Byzantine fault tolerance, we don't want to make it dependent on a single administrator in one place, because that single administrator can just revoke everyone's permissions and do all sorts of other things. So from the perspective of the people looking at this in large companies, blockchain is very much a tool rather than an ideology. There is no desire in these companies to change the way the world works in any kind of fundamental way. The desire is to find something which is useful for them in terms of solving the problems that they need to solve in running their businesses. And if at this point someone has decided that this is not interesting to them because they're a cryptocurrency enthusiast, completely understand that, but that's the way that these people think. Yeah?
So would you distinguish, like, so the distinction between this and just a data, what's it called, a distributed database, is that one company versus, let's say, 10? Or, more than one company?
Well, we'll talk later on about use cases within a single company, but generally speaking, the classic idea would be shared between multiple companies. Yeah. So, tomato number one are people who say, well, this is just a slow database. Sure, yeah.
What is the meaning of miners in a small group?
So it's not mining in the sense of solving a difficult computational problem to create a block. It's mining in the sense of building a block. So you might want to call them a validator instead. And that's why I put miners in quotes often in a presentation. So, first tomato thrown in, this is just a slow database, right? We've taken databases which have been existing for decades. There's tons of work and research and optimizations gone into databases, and you've just made your database really, really slow by building it around this kind of architecture. That tomato doesn't hit home, because if you look at a traditional database which would be shared between multiple companies, this is how it would work. The database would sit in a single organization, which would effectively act as the trusted intermediary for that group of companies. They would be in charge of the database, and any access to that database from external organizations would be through an API or a querying interface or something like that, so that these external companies do not have any kind of meaningful control over the database. The central company in the middle can decide to remove data, it can decide to add erroneous data, it can essentially do what it wants. So that's a traditional database, that's how a traditional database would be shared between a group of companies. This type of database, which you might want to call a peer-to-peer database, is different. Everyone has a full copy of the content of the database or the ledger. Everyone is connected to everyone else. If it's a small network or if it's a large network, we might not be fully densely connected, just like in cryptocurrencies. But we have a peer-to-peer network that isn't dependent on any individual company and any individual connection. Transactions are being transmitted and broadcast over this network, and they're propagating through the peer-to-peer connections. And transaction represents an individual event. And then we have a separate stage called a block, which is essentially, as we all know, a group of transactions which are being validated. So architecturally, it looks very, very different to a traditional centralized database that's being shared. Yeah.
Companies run an architecture like this: Google, Yahoo, Facebook, with Paxos, Zookeeper, etc. So how is this different?
So that's within a single company. It's not Byzantine fault tolerant.
But that Byzantine fault tolerance, the paper was published in like 1989.
So what's the question is, people have been doing this before. Yeah. I would agree with you, and I'll talk about that later.
Okay.
Yeah. So, what is the purpose of a blockchain here? The blockchain is the mechanism by which we ensure consensus between peers. It's essentially groups of transactions which are grouped together in blocks, and then each block is linked to the previous block. And so I think we probably shouldn't be calling these things blockchains, even though everyone is. We should be calling them peer-to-peer shared databases, because the blockchain is just what happens on the inside. It would be a little bit like calling Oracle a B-tree. Because if you look at traditional relational databases, they use B-trees extensively as a data structure to enable them to do what they do, but no one calls them a B-tree because that's not a very descriptive name for their purpose. And I think it's the same thing here. So if we accept that there is this notion of a database which is directly shared between separate non-trusting parties in a peer-to-peer way, a set of requirements drop out of this. And these requirements happen to be very similar to what we see in cryptocurrencies. Number one, we need each transaction to be represented as an individual packet that travels across the network. So, because a transaction is something that has to be atomic, it has to either succeed or fail as a whole. Because it's a peer-to-peer network, we can't have bits of transactions moving around. We want to have a single transaction appear as a single packet that moves across the network and is either accepted or rejected by every node. Because it's a peer-to-peer network, when a node receives a transaction, it doesn't know, based on where it received the transaction from, where that transaction originated. Because it may not be from the original sender, and it can't necessarily trust the node it received that transaction from. So as a result, every transaction needs to be digitally signed in such a way that the originator of that transaction is known. And in addition, if our transactions are going to allow us to modify the database, we need data in the database to be tagged with public keys which correspond to the signatures generated by the private keys that are on the transactions. So if we have, for example, a transaction that moves funds in a database that represents a ledger of funds, we need to be able to tag data in the database by saying this particular row in the database belongs to a certain party. Here is that party's public key. And the only way in which this data can be modified or deleted is by a transaction that's been signed by the private key corresponding to that public key. And we need a mechanism like that inside in order to create a peer-to-peer shared database. Lastly, we have here a database which can be written by multiple non-trusting parties. Well, if we're going to have multiple non-trusting parties, we need to have rules about what kind of transaction is valid and what kind of transaction is invalid. Because otherwise people will just do transactions that are good for them and that are bad for the others. So we need rules, or what I like to call transaction constraints. Traditional centralized databases have many different types of constraints, but they don't have transaction constraints. They don't have rules you can define in terms of, let's look at what a transaction does as a whole, and we have at the data level a rule which says, is this transaction valid or invalid? But this type of database does have that. And there's two popular styles of transaction constraint, Bitcoin and Ethereum-style, that we'll look in a minute. And obviously we also need a consensus mechanism in these kind of databases as well, and that goes back to the question about Paxos. And it's true that Paxos is a perfectly good consensus mechanism for this kind of thing, but there are other characteristics of these kind of shared databases which aren't in the Paxos algorithm, which are separate features of these kinds of databases in terms of transaction rules and in terms of signed transactions. So what does the transaction constraint look like? So there's two common types of transaction constraints in the cryptocurrency world right now. If you excuse me, I'm not yet including things like Tezos, which are still being developed. And you see the same things in permission blockchains. Transaction constraint type 1 is demonstrated by the following picture. Each transaction deletes some rows in the database and creates some rows in the database. When a Bitcoin transaction spends some unspent transaction outputs and generates some new ones as a result, you can look at that as the deletion of some rows in the ledger and the creation of some rows in place of those rows in the ledger. And Bitcoin has rules about whether or not a transaction is valid in terms of well, if the total amount of money in the rows generated, or the total amount of Bitcoin is less than or equal to the total amount of money in the rows deleted, then that is a valid transaction. So this is a rule which says look at the set of rows deleted, look at the set of rows created, feed those sets of inputs and outputs into some black box, and that black box says, is this a valid transaction or is this an invalid transaction? And that's one way of creating transaction constraints or transaction rules. I should just add, if we're talking about databases, the act of modifying a row in the database is equivalent to deleting that row and replacing it by a new row. So if we're talking about modifying rows in a database, we can still think about that as deleting and creating a row. And those of you who know how things like MVCC concurrency works, that's exactly what happens behind the scenes. So that's one type of transaction constraint, a black box that looks at the inputs, looks at the outputs and said, is this a valid transaction or not? The second style is what we call today smart contracts, so that's probably not a particularly good name for them. It's where we have code embedded inside the blockchain, which is essentially saying this piece of code owns this piece of the database, and the only way in which the database can be modified is if that code decides to perform modification. So this is taken from the most simple smart contract you can find in Ethereum. It's a basic smart contract to manage a subcurrency. Someone sends a message to the smart contract to say, please transfer funds from account A to account B. So Ethereum checks that account A matches the signature on the transaction. It checks that account A has enough money. And if account A has enough money, it deducts from account A and it adds the money to account B. So this is another way of representing transaction constraints where we essentially have code embedded inside the blockchain which says no one can touch my database apart from me and I get to choose what happens to my database. And that's another equally valid way of doing transaction constraints. There are advantages and disadvantages compared to Bitcoin's way in terms of concurrency and in terms of flexibility. For those of you with a background in databases, you can pretty much look at smart contracts as a stored procedure which is enforced. Right? We have stored procedures in regular database platforms today, but the difference in Ethereum is you cannot directly modify the database. You have to go through these stored procedures. Yeah.
Does this specifically increase privacy?
Not at all. No.
It's just a different design.
Yeah. I mean, this is perfectly. If you look at, for example, if we're talking about simple blockchains that don't have privacy features built in, like Ethereum and Bitcoin, anyone examining the transaction flow in both can see exactly what's happening, and the code also is perfectly visible. Okay. So if I wanted to pigeonhole permissioned blockchains in the space of IT tools, I would just say this is a new type of database. Right? There are many different types of database. We have traditional relational databases. We have NoSQL databases like MongoDB and so on. We have in-memory databases. We have search-oriented databases. We have graph databases. And this is a new type of database. This is a peer-to-peer shared database. And none of these other products can do what these databases can do in terms of being able to be safely shared across boundaries of trust between multiple organizations. Tomato number 2 is that these are not immutable, right? These databases, the validation is built on trusted parties, and therefore it's not immutable. So let's talk about how mining, and I put mining in quotes, how does it happen in private chains? Well, there's many different ways to do it. I'll talk about how it works in our product. But they're all essentially philosophically equivalent. So in our product, every block generated is signed by the miner or the validator that generates that block. Okay? Only permissioned parties are able to sign blocks. So this whole business of Sybil attacks and having to worry about preventing minority control of the chain is solved in a much more straightforward way than you need in open proof-of-work-driven blockchains, because we simply have every block has to be signed by a miner. There are rules and permissions about which miners are valid, and there's no ability for anyone to impersonate anyone else, because if I'm impersonating someone else, either I've stolen their private key, in which case, well, that's a violation of the whole rule of the network, or I'm using some address which doesn't have permission to mine blocks at all, and no one's going to pay attention to my block. So much more simple. And then we have a constraint in multi-chain called mining diversity. Mining diversity is essentially a round-robin scheme with a little bit of leniency. So the round-robin scheme essentially says you cannot mine a block unless a certain number of other blocks mined by others have passed from the last time you mined a block. Simple as that. So here the green miner mined a block, then the blue miner mined a block, then the red miner mined a block, then the green miner is trying to mine another block or add another block to the chain. Everyone on the network says, no, it's been too soon since your last block. That's not accepted. The purple miner comes along, and then the green miner comes along again. So it's essentially a round-robin scheme, but it's not pure round-robin, because the problem with a pure round-robin scheme between a set of permitted validators is if one of them goes offline or the computer stops working, then the whole blockchain freezes up. So it's in a way to, and you can customize it in the platform, you can essentially decide how strict or lenient you want your round-robin scheme to be, so you can balance the risk of collusion between a group of miners against the risk of technical failure of some of those miners. And we recommend for production at least 50%. In other words, you want at least 50% of the permitted miners to participate in a chain in order to render that chain valid. So when we talk about immutability, people often think immutability is yes or no. Yeah?
On the previous slide, do you have any guarantee
Well, it would need, in order to cut the green one off, you'd need enough of the other ones to decide to build a chain that cuts them off that would fulfill the mining diversity constraints. So yeah, if enough of them decided to do so, say 60%, then they could cut someone off. But you'd need that malicious collusion. Otherwise, at some point, one of the other miners would accept a block that comes from the green one. So immutability is not binary, right? There's no such thing as perfect immutability, not even in the strongest hashing block, in the strongestly hashed blockchain, which is the Bitcoin blockchain. Transactions in any blockchain and in any system are not written into the mind of God. And it's important to understand that immutability is not a yes or no question. Immutability is about saying what secures this particular record and what risks are there in terms of this record being violated. And there is always some kind of risk. For example, in the blockchain, if every single Bitcoin node shut down and wiped its hard disk, the transactions would be gone, right? So that's obviously a very unlikely type of risk, but nonetheless, that is a type of risk. So in public blockchains, I'm sticking now for the purposes here to proof of work public blockchains, the content of the blockchain is secured by proof of work, by having the blocks being generated by people that solve a very difficult mathematical problem that actually costs money and costs electricity to solve. But the Bitcoin blockchain and others can be muted or mutated, whatever the word is, if 51% of the hash rate decides to do so. So if right now the Chinese government is mining the Bitcoin blockchain with a higher hash rate than the rest of the network put together, and we don't know about it, they're doing it in secret, and in 6 months' time they decide to broadcast their fork to the world, their fork, which contains whatever transactions they wanted to contain, will become the network majority according to the rules of Bitcoin. So there is a risk there. And so the threat when we talk about immutability in public blockchains is somebody very rich and very highly motivated deciding to invest the necessary resources to undermine the chain. It's an economic type of immutability, ultimately, in terms of economics and in terms of motivation. Private blockchains are different. They're not secured by proof of work. They're secured by this form of distributed consensus, by a kind of majority voting or a majority control between a group of permitted validators. They can also be corrupted or mutated if a majority of those validators decide to do so. In other words, if a majority of the validators decide to say, we're going to rewrite history of this blockchain going back several months, and enough of them decide that that is the true chain, then they can also retroactively change history. So the threat in a private blockchain is validator collusion, right? Is that enough of the validators get together and they decide they want to undermine the history of that chain. Now that's also a threat. Now these two types of threat scare different people, and different types of people are comfortable with them, right? People who believe in censorship-free finance and who don't want to have trusted parties, they like the first type of immutability, where it's very, very expensive, even if possible, for the security of the chain to be undermined. People who are in large companies, who know who each other are and who sign contracts with each other, they're very comfortable with the second type of immutability, because if something like this happens, they've got a full audit trail of what happened, and they can essentially take somebody to court. And they're not comfortable with the first type of immutability because they don't want to be at risk from some unknown third party that suddenly decides to invest enough money in enough hashing power to undermine the chain. So immutability, the attractiveness of different types of immutability depends on who you are and what your own incentives are. Charter number 3, this is not a blockchain, okay? Or this is not a blockchain in quotes. So, obviously there are many differences between public and private blockchains. Public blockchains don't have a permissions model, private blockchains do. Public blockchains are generally designed around the idea that there is no censorship of transactions. Many people think that's the main purpose of them. Private blockchains, transactions can be relatively easily censored if enough of the validators get together and decide that they don't like a particular transaction. There is a native cryptocurrency to public blockchains. Obviously, there isn't in private blockchains, or I should say generally there isn't. The governance structure, we've heard a lot about this. The governance structure of the two different types of blockchains are very, very different. One is based on some kind of objective, economic, or voting mechanism that's available to the whole world, and one is based on a group of trusted parties who are governing the chain. And proof-of-work consensus tends to be used in public blockchains and not in private. So there are a lot of differences, but there are also a lot of similarities. We still have a peer-to-peer architecture in both cases. We still are looking for Byzantine fault tolerance. Public key cryptography is an absolutely core feature of both of these chains, asymmetric cryptography. They both have some kind of transaction constraint, some way of restricting what's valid, and they both use a chain of blocks to represent consensus, even if that chain is generated differently. So we have two types of things here, some similarities between them, some differences between them, and for those of you who know anything about the philosophy of language, anyone who this guy is? I know I'm in a... Ludwig Wittgenstein, right? So Ludwig Wittgenstein is very interesting because he basically came along and said, you know, people argue till they're blue in the face about what certain words mean, but actually I say that words mean the meanings that people use them by. And on that basis, I think it would be perfectly legitimate. If no one used the word blockchain to refer to these enterprise blockchains, then I think we'd be silly calling them blockchains. But many people do use the word blockchain to refer to these. And because you can make a fair case that there's enough in common between that type of blockchain and the cryptocurrency blockchain, and because these enterprise blockchains do use a chain of blocks, I think it's fair to use the word blockchain to describe these systems. And that's why, even though lots of people don't like this and there's all sorts of arguments about it, I think it's a reasonable use of the word, and I think it's fair to say we've got open and closed blockchains, or public and private blockchains, or permission blockchains, and so on. So I think Mr. Wittgenstein can stare down that tomato. Okay, the next tomato, number 4, is, well, I've described a very interesting theoretical system, but it's just not useful for anything, right? Why would anyone want a system like this? Why would any group of organizations want to create a kind of database consensus system that works in this way? So here's the use case that lots of companies, including our own, started by thinking about, and lots of the conversation started thinking about this use case. We have a system here for moving money between companies. Okay? We have multiple companies who are connected to and running nodes on a particular blockchain. Some kind of money is issued into this blockchain as some kind of token. So just like you can issue tokens today onto the Ethereum network, you can also issue tokens onto a private blockchain. Who's issuing the tokens? Well, that could be anybody, but it has to be somebody that all the participants are willing to rely upon. So people think that perhaps one day central banks, government banks will issue money onto blockchains, and therefore the tokens that people are transacting will be just as good as a 20 shekel note in your pocket or a £5 note in your pocket. People think that might happen. You set up a system like this, then these companies on this system are able to perform instant transfers of funds between each other, right? They can simply send transactions to the blockchain, and the money represented by these tokens instantly moves from one company to the next. And what's nice about it is we have settlement in the full meaning of the term, and the financial meaning of the term takes place in seconds, right? So there's no intermediary here. There's no question of having to reconcile systems between different kinds of databases. We have a system which essentially, in a matter of seconds, comes to consensus over the question about who owns what money. And reconciliation, which is something that lots of companies spend a lot of time on, worrying, well, do my database records match your database records, and do yours match the other side's database records? Reconciliation comes for free in a blockchain, because a blockchain is a reconciling database, a reconciling distributed database. It automatically, all the time, acts to make sure that everyone is in agreement with each other after a few seconds. And one of the things that people like about this idea is if this is money moving around in a field which a regulator is interested in, a regulator can essentially plug into this blockchain and run a read-only node, watch the flow of transactions, and instead of having to come to each party in the system and say, well, give me your records, and let's kind of cross-reference that with the records of the other parties and make sure we understand what's going on, the regulator can watch the system in real time and see exactly what's happening. So this was a very attractive idea to many people when the conversations in this area started a couple of years ago. Technically speaking, it's easy to do. You can do it easily on our platform. You can do it easily on other platforms. But there's only one big problem with it. And the big problem with it is that, generally speaking, this use case falls down when it comes to confidentiality. If you look at companies creating these kind of networks to move money around between each other, they can perfectly well do it, but they don't really want all the other participants in the network seeing every transaction that takes place. Right? If you imagine, for example, to take the classic case of 10 banks wanting to move money around between each other in this way, if 2 banks conduct a transaction, they probably don't want the other 8 banks to see that transaction. And we could talk about confidential assets and zero-knowledge proofs and ZK snarks and all these things that you've discussed this week, and there are many ways to partially or almost completely solve this problem. But ultimately, there's still a signal there, right? A transaction takes place, that transaction is represented by something on the blockchain, even if no one knows what that thing is, and you can start to correlate all sorts of things and look for signals to work out what's going on and what your competitors are doing. So this kind of use case, for the most part, has fallen down when it came to the kind of reality check. And with a few exceptions, you don't hear much talk about this kind of use case today for enterprise blockchains. So where are they useful? And so the way in which I like to describe this when I'm talking to kind of people who are looking at a blockchain use case is that whenever you have a blockchain use case in mind, consider the alternative of a centralized database. Always consider the alternative of a centralized database straight away, because anything you can do on a blockchain in terms of a data processing activity, you can do on a centralized database. And anything you can do on a centralized database, you can equally well do on a blockchain. But these are genuine technical alternatives or technical options for the same types of problems. So what are the trade-offs here between these two alternatives? So the big thing the blockchain gives you, which I'm sure we know by now, is disintermediation. It's this ability to have a single view of the truth maintained between a group of parties without any individual party being in charge of that truth and having responsibility for that truth. And that can be a nice feature. And the big disadvantage that we've also discussed is confidentiality, is the fact that in this type of system, in a distributed peer-to-peer shared database, much more information is getting to all of the participants than in the case where we have a centralized intermediary running a centralized database. Because in the case of a centralized intermediary, only that intermediary and the transacting parties see a particular transaction, and the rest of the participants in the network have literally no idea that anything happened at all. So that's the key trade-off. There's a couple of other lesser trade-offs. One nice thing about enterprise blockchains is that they give you robustness on the level of multiple organizations. So if you look at how companies today deal with the possibility of data loss, they have to create their own backup systems and their own failover systems. If something goes wrong with their primary system, it all falls over and fails over and moves to the backup system. If you use this kind of peer-to-peer shared database, you can actually just recover from the network anything that you lost. So as long as you're willing to trust the network in terms of the majority of the network, then if your systems go down, you don't need to have a backup of your data locally. You can essentially kind of rebuild your data from the other participants in the network through the blockchain. And another kind of secondary disadvantage of this type of database is it will always perform less well than a centralized database. And it will always perform less well than a centralized database because what a node has to do in a blockchain in terms of processing transactions is all the things that a centralized database has to do in terms of processing transactions, but it has to verify cryptographic signatures, it has to worry about consensus, maybe it has to do roll depending on the type of blockchain you're using. So it's always going to have to work harder. And one of the key things that people think that blockchains is a solution to scalability of databases, it's absolutely not. It's the opposite. If you want to solve scalability, you go to a kind of traditional distributed database. Blockchains actually are always going to be slower than centralized databases. And you can kind of expand the conversation a bit further because if you think about the ways in which companies interact with each other when they're exchanging data, there's three things they want, right? They want reconciliation. They want to make sure that all their systems agree with each other. They want disintermediation. They ideally don't want someone else to be in charge of that process. And they also would like confidentiality. They'd like information to only get to the parties that want to see that information. And unfortunately, like many things in life and many theories in computer science, you can't have all three things that you want. So if a group of companies get together and they want to integrate with each other through data, they need to decide what's more important to them. If they really want confidentiality and reconciliation, and they're willing to forego disintermediation, then a centralized database through an intermediary is a good solution for them. If they want confidentiality and they want to have disintermediation and they're willing to forego guaranteed reconciliation, then they can use some kind of messaging platform where essentially each company communicates on a point-to-point basis with the other companies in the network. But if they want reconciliation and disintermediation and they're willing to forego some confidentiality, then a blockchain type of integration architecture could be the right thing for what they're looking for. And so it's just a matter of a trade-off, essentially, yeah.
What about security? You're counting on a closed garden of all the companies that participate, but Bitcoin adds security by the method.
So explain what you mean. Are you talking about proof of work security?
Yes.
So we talked about this before. So the security in this kind of network is based on trusting a majority of the validators. You don't have to trust any individual one.
Swift was hacked.
Yeah, Swift is a centralized intermediary. That's different. Swift is a centralized company. So if someone manages to corrupt the data in Swift's database, then everyone's had it. But we're not talking about a single party maintaining control of the data in the database. We're talking about a group of parties, some kind of federation of validators maintaining control. So if one of them is hacked, then that hacked node cannot destroy or corrupt data in the database on its own.
You have to hack a majority of keys, in theory, right?
You have to hack a majority of the keys of the validating
Which
nodes.
are in different places.
Which are in different places, exactly, yeah.
I think the Swift hack was client-side, like
You
someone
may
accessed
be right.
someone's keys and did a transfer.
Yeah, in which case, this wouldn't help with a client-side hack. If one of the nodes has a key which protects its funds and that particular node's keys are hacked, then those funds can be spent. That's true. Okay, so let's talk about real use cases. Where does this actually turn out to be useful? And this is based on the fact that we have a platform which is pretty popular and is downloaded and used by lots and lots of different people. And so we hear a whole ton of blockchain use cases. A whole ton of them do not make sense. But these are the ones where we do see sense and we see people building systems for production. Number one, if a process spans multiple geographies and multiple legal jurisdictions, often it's difficult for the parties in that process to decide where the database that's responsible for that process is going to sit. Where is it going to sit geographically, and under which particular legal system it's going to sit, right? If you have a manufacturer in China, a shipping company in Europe, and it's being delivered to a retailer in the US, well, where's that database going to sit? Who's going to control that database? So we have a problem in some of these cases with creating a centralized database to manage a process. You use this type of peer-to-peer shared database, and we have an ability to share the control over the database between multiple parties, and suddenly no one has to give over control to any other specific party. Number two, aggregation of data. So if multiple parties are generating data, and they want to bring that data together and make sure that they're all seeing the same aggregated version of that data, blockchains are particularly well suited because there is no issue of confidentiality here. All the data in the chain is meant to be visible by all of the participants in the chain. And what we're avoiding is the need to create some external third party which is responsible for aggregating that data and redistributing it, or the need for everyone to maintain a replica of everyone else's databases. So it's a different way infrastructurally to perform aggregation of data between a large number of parties. Number 3 is lightweight financial system. So a lightweight financial system is a financial system where the stakes are relatively low. What does this mean? It means that A, we don't want to spend a lot of money on creating this trusted intermediary which holds the central ledger that keeps a record of who owns what, because the amount of money and investment and time and contracts and setting up the organization of doing that isn't justified by what we're looking at. On the other hand, it's lightweight because we're willing to give up the confidentiality, right? The participants in this kind of system are willing for other participants to see what's going on with their money because the stakes are relatively low. So the trade-off here, if we're willing to give up some confidentiality and we want to avoid the cost of setting up a trusted intermediary to maintain a central ledger, the trade-off here falls in favor of using this kind of blockchain solution. And the last thing is notarization and timestamping. If a group of companies come together and they want to create a shared archive that notarizes and timestamps when particular documents existed, so that if in 3 years' time there's a dispute about something, they can all pull up the shared record and say, no, look, here's a timestamp in the blockchain showing the document was there at a certain point in time, then that, again, is a good use of a blockchain. And the nice thing about this is if confidentiality is an issue, often we just put hashes of documents in the blockchain. Right? We might put a document in the blockchain in full plain text if we want to actually have the blockchain store it and replicate it to all the nodes. We might encrypt it if we want everyone to have a backup of it, but only certain parties to be able to see it. Or we might just hash it and put that small 32 or so byte hash in the chain, which is enough for anyone to validate the document in future, to validate that it existed at some point in the past, but no one can obviously reproduce that document from the blockchain itself. They need to get an original copy of the document. That's another case where we see this type of blockchain being genuinely used. And I was asked before about internal blockchain use cases, and the surprise I had in working in this field is that there are cases where blockchains are also being used inside a single company. Now, why on earth would you put a Byzantine full-tolerance database inside a single company if you could just put a centralized database in the headquarters of that company instead? Why would you create this type of database inside a single company? And it turns out that there are certain cases where you would. Number one, often a single company isn't really a single company. This is true especially in the finance world. Often what appears to us as consumers as one bank is actually many, many different institutions, each of which is a separate legal entity, each of which is under a different regulatory regime. And when these subsidiaries move money between each other, they want to maintain meaningful control over their funds more than just having something written in the centralized database in headquarters which says I own the funds. They want to have more meaningful control of that, and it's demanded of them to have that control by regulators in certain cases. So if we want to move money around inside a complex organization between multiple subsidiaries or different parts of that company, then a blockchain can be a good solution. And the confidentiality problem here often falls away because these different parts of that particular company don't feel the need to hide anything from each other. Right? They're not competing with each other. They're often working in completely different geographies. But nonetheless, they do need to maintain control over their own funds in this kind of system. That's number one. Number two is to prevent corruption. So there's quite a lot of use cases in the developing world where essentially a government wants to run some kind of program which requires a database on the back end, and they do not trust any particular physical location in any particular department to run that database, because people can be paid off and can be bribed in order to modify and delete data from that database. So the solution for these kind of governments, and we'll leave it as an open question whether or not Israel would qualify as the kind of government that would need this. The solution for these kind of governments is to place multiple nodes in multiple geographical locations, in multiple departments, and these nodes collectively secure the information in the database. So that if one person in one place is bribed to do something to change an entry in the database or modify an entry in the database, then maybe they'll do that change, but the previous data won't be removed. The previous data will still be there, and there'll be a clear audit trail showing what happened.
Right, but don't databases do logging?
Yeah, but who's gonna stop you deleting a log? A blockchain is a log.
But without mining, so you could also unwind the blockchain.
If you've got enough of the validating nodes to collude, then you could unwind the blockchain. A blockchain is a transaction log. That's exactly what a blockchain is. That's what the content of a blockchain is. But it's a transaction log which is secured from multiple places by consensus. And the last thing is to protect against cyber attacks. It's important to be clear here. If you run a blockchain type system, then each node, if that node is attacked and becomes under the control of an adversary, then there's certain things that adversary can do and there's certain things that adversary cannot do. The adversary can do anything in the name of that node if the private key is stored together with that node. The adversary cannot delete old data from the chain because that has to be done by consensus between multiple validators. And the adversary can read all the content of the chain. So this is where we're very worried about data being modified and corrupted historically, and we're not so worried about data being read by an adversary. For those types of risks, this is a suitable architecture. Yeah.
Do you know any uses
Industrial espionage? I don't, and the problem with blockchains is that they make any confidentiality or secrecy problems worse than they were before. So if we're worried about someone reading data, stealing data, then a blockchain is not going to be the direction you want to go. And you want to go through splitting the data, in multiple places and secret sharing and that kind of thing. But a blockchain specifically is not going to help you with that. Okay, next tomatoes, this is nothing new. Okay, this was raised early on. Absolutely right, there's nothing new about this. Technologies which look extremely like permissioned blockchains have existed for decades and have been used in production. I had a very interesting conversation with the founder of this company, Gideon, who built a system like this 20 years ago to secure the information regarding vulnerable children. And there's a company called Gartime which has been doing this kind of thing before anyone was talking about blockchains. So it's true that on a purely technical way, the idea of securing a set of records through some kind of consensus of signatures, whether it's round robin or whether it's practical Byzantine fault tolerance or something else, that is not a new idea. That has existed for decades. But there are some new things. So one of the things which I think is new is the Bitcoin transaction model is very interesting. Because the Bitcoin transaction model essentially is a way to allow concurrency over a network while still preventing transactions from conflicting with each other at the time of validation, and that is new. And also Ethereum's ability to represent the entire state of a database through a single hash, which can then be efficiently modified through small changes anywhere in that database. As far as I know, that's new in terms of database architectures. But the main thing really is that what's happened in the last few years is that people have started, including us, to productize this thing. So whereas before people were building systems like this very much on a piecemeal non-token basis, now there are platforms emerging which essentially allow you to do this out of the box. And that essentially makes life much easier for people who are trying to build these types of systems. So I don't know if I'm going to get to all my tomatoes. So I'll show you a couple of cartoons which answer the question, is this overhyped? These are actually non-original Dilberts. They've been modified. They're old Dilberts that have been modified to talk about blockchains. And so I think the idea that this is overhyped is absolutely spot on. Blockchains are overhyped. Most things you read about permissioned blockchains are nonsense. If you just look online and read them, they don't make sense. Most of the use cases people talk about don't make sense. This is a specific tool which is suitable for a specific set of use cases, and it's not going to absolutely transform the enterprise IT world, but it has its uses. So I was going to talk briefly about our product, but I'm going to skip that, just talk about some of our partnerships and some of the production projects that have been running our product and what you can do on a permissioned blockchain. The last thing I want to talk about, because I've got a couple of minutes, is the last tomato, which is that I have no purpose in speaking about this at a conference which is about cryptocurrencies, right? This is all very interesting. It's a new enterprise IT architecture, but there's literally nothing whatsoever in common between the kind of blockchain or enterprise blockchain that I'm talking about and cryptocurrency networks. And I think that's partially true and partially untrue. First of all, our take on cryptocurrencies as a company is we believe they will persist in the long term. That's what it looks like based on what we see today. I have absolutely no idea what the price of a cryptocurrency is going to be next week, never mind in 5 years' time. It could go up a great deal, could go down a great deal. We have no idea, and I don't think anyone can really predict it because the answer depends on mass psychology. It's essentially a cryptocurrency is worth whatever enough, depending on the number of people that think they're worth something. That's what determines the ultimate worth. Despite the fact that this is not obviously anything to do with the usage of cryptocurrency, there is a lot of technical common ground between the kind of systems that we're talking about and cryptocurrencies. The first thing to recognize is that a cryptocurrency is a decentralized database. Right? If you look at Bitcoin, what Bitcoin is, it is a decentralized database. In the case of Bitcoin, it's a database that tracks who owns how much Bitcoin. That is the data in the database. But it's essentially a database. That's what it is. It's a ledger. And so obviously, if we're talking about decentralized databases of different form, there's a lot in common with them. We also expect, over the long term, a lot of cross-fertilization of technologies between the two worlds. I think it will generally be in the direction of from cryptocurrencies to enterprise blockchains, because the cryptocurrency user base is much more risk-friendly than enterprises. Enterprises are much more risk-averse. They tend to like to see something working for many years in the cryptocurrency space until they think about adopting that kind of technology for enterprise blockchains. One of the things that I'm most interested in following is the kind of the ZK snarks and the zero-knowledge stuff, because I think that potentially, when it's proven and has been running for long enough, could be used to solve the kind of issues I talked about in the interbanking use case that I talked about earlier. So I expect there'll be a lot of cross-fertilization between these two fields because they have a lot technically in common. However, in terms of applications, I see literally no common applications between cryptocurrencies and enterprise blockchains. I've not yet heard of a use case for one that I thought, well, you might do that on a cryptocurrency, and you might do that on an enterprise blockchain. The use cases are completely separate. But that isn't something that should scare us, because there's many cases in computer science where the same technology is used for many different things. TCP/IP is used for home networking, and it's used to power the whole internet, for example. Or compression based on repeating sequences is used for genetic data, and it's used to make websites quicker, and it's used to do all sorts of other things. So we shouldn't be scared of that fact, but we just need to admit it and be clear about it. This is a dual-use technology, which has no commonality between the two use cases, yeah.
So according to you, what do you think differentiates the different cryptocurrencies? Is it the mechanism for privacy? Is it, what's the difference?
Between the different cryptocurrencies?
Yes.
I mean, there's a vast number of differences between, any number of them. So to take the two largest ones, Bitcoin and Ethereum,
Right.
the Bitcoin is essentially very kind of, as was mentioned earlier, very conservative, and in practice seems to have turned into some kind of internet gold, whereas Ethereum is kind of much more experimenting and is a platform which people are launching many, many other things. But I guess that question is, I could talk for hours about that question. It's not really in the scope of my talk because there's a vast number of differences between all sorts of different cryptocurrencies out there. Our particular architecture is a derivative of the Bitcoin architecture, and there's also people who are doing derivatives of Ethereum, like the Enterprise Ethereum Alliance, and there's also permission platforms like Hyperledger that kind of built something from scratch. So there's all sorts of different things going on. So blockchain, just to summarize, blockchain is a new approach, a new option for integration between multiple enterprises. That's what blockchain or permissioned blockchain is. Cryptocurrencies are, depending on who you ask, a new type of gold, a new type of finance, or just another version of the tulips. And I think we don't know which one of those things is going to end up being true, but whatever happens in the cryptocurrency field, the question as to whether blockchains are helpful for enterprises is really a completely separate and a different question. So I don't know if I've got any more time for questions, but that's the end of my content.